Hi all. In Unit 7, we have so far talked about equilibrium constants Kc based on concentrations. And those concentrations are in molarity. But actually, you can also calculate a different type of equilibrium constant using partial pressures. If all of the components in the equilibrium expression are a gas. Let me show you a couple of examples. We'll call this general examples, or just calculating Kp. If you have a general equation, let's say A gas plus 2B gas in equilibrium with the product, let's say C gas. If you're given the partial pressures, you could calculate a Kp that looks like this. So you've done partial pressure calculations before. You have a total pressure, and you figure out the mole fraction for each component, and you multiply the mole fraction times the total pressure to get the partial pressure. If you have those partial pressures, remember equilibrium constants are products over reactants. We're going to show it like this. Partial pressure of C subscript over partial pressure of A, but we're going to multiply it also with partial pressure B, so I'll put parentheses. Partial pressure of B, and yes, you're still going to use the coefficient as an exponent 2 squared. What can we say about this equation? Well, first of all, just like Kc, this Kp is going to be unitless, and the P stands for pressure, or you could say partial pressure. I'll discuss this a little bit later, but for a given reaction, Kp normally is not equal to Kc. Sometimes it is, and I'll show you those conditions later. Should we use a real reaction? Let's try. So right now we're just writing the equilibrium expression. Oh, the other thing is equilibrium expression for Kp. The other thing is that these partial pressures should be in atmospheres. Okay, you'll see why in just a bit. Let's do one example. Let's use real. Actually, we're not using real chemicals. Yeah, let's use real chemicals. Let's use. Do I want to use real chemicals? Yeah, let's try this. CH. Already messed up. CH4 gas, methane, plus H2O, and I'm going to make this liquid. In the previous video, you know that we discussed. Do not use liquids and solids in the equilibrium expression. Next, CO gas, plus 3H2 gas. I think it is balanced. 6 hydrogens. Okay, good. Well, let's actually also put some values. So let's say the partial pressure of each gas is going to be listed here, and it's the partial pressure at equilibrium. Now we could get obviously a QP, right? Q typically is the conditions where the concentrations or partial pressures are off equilibrium. But let's just focus on at equilibrium to figure out Kp. And also there's a temperature, because equilibrium constants are temperature dependent, and I'm just going to randomly pick, I don't know, 300 K. Okay, here are the values. Let's use 0.045 atm. Okay, and we're taking these numbers as at equilibrium. This is a liquid, so there is no partial pressure. 0.018 atm and 0.070 atm. So you are still allowed to calculate Kp even if one of the components is not a gas. I think, I'm pretty sure that if one of the components is aqueous, you cannot use Kp. Okay, so whatever is in the equilibrium expression has to be a gas. But you know that liquids and solids are not in equilibrium expressions. I suggest that students write out the expression first and then plug in the numbers. So this is Kp, partial pressure CO, times the partial pressure of H2 cubed divided by the partial pressure of CH4. Okay, now we can plug in numbers. If you want to pause the video and calculate it yourself, that'd be great. Let me plug in my numbers. It's only that value is cubed. What would I do first? I would do the cubed first. 0.070 raised to the third power times 0.0118 equals divided by 0.045 equals. Alright, so the Kp equals 1.37 times 10 to the minus 4. No units. Okay. That, we'll call this problem 1. Okay. Calculating Kp. Is there anything else I want to say about this? No. Let us try another problem. Oh, how about this problem? In this problem, you're going to solve for the partial pressure. You know, in this problem up here, we solved for the Kp. So here we're going to solve for a partial pressure of x. It's going to get complicated later. Right now we're going to solve for one of the partial pressures. You actually can solve for multiple partial pressures for different compounds, but that is a little more complicated and will be discussed later. This is the problem number 2. 2 pH3 gas plus, not plus. That's all we need. Somehow those two molecules are going to combine to make a P2 gas, plus another time we see 3 molecules or 3 moles of H2 gas. Okay, all of these will be in the equilibrium expression, and this is what I'll give you. These are going to be the partial pressures of the gas at equilibrium, 750 K. Okay, I am only going to give you this one and this one. And the question is, what is partial pressure of the H2 gas? I would need to give you the Kp. Kp equals 19.6. You want to pause your video and try that one. Solve for Px, x meaning hydrogen gas. Okay. Again, I would suggest drawing out the expression. Okay. P pressure, partial pressure of P2 times partial pressure of H2 cubed, but that's what we're looking for. And then partial pressure of phosphorus trihydride squared. I'm going to plug in the numbers. I still have 19.6 here. I'm running out of room. 0.215, and we'll simplify this to x cubed, right? X is partial pressure of H2, and then 0.112 squared. When we get x, x is that answer. How would I do this? Don't forget we have 19.6 on the left. I would square this and then cross multiply first. 0.112 squared times what is it? 19.6 equals. And then I got to isolate x. So I'm going to divide by 0.215 divided by 0.215. Okay, so that number equals x cubed. So in my calculator I guess it's the cube root instead of the square root, we're going to put 3, that symbol there, of the answer equals? Okay, that's the number I was expecting. 1.046. Oh, and it is a pressure, partial pressure, and it is in atmospheres. Okay. If these were given in torr or millimeters of mercury, I think you do have to convert them. You should convert them to atmospheres. Okay. Or else the Kp will definitely be different, or the X would be different. Okay. Last part, part C. Well, we have Kc, and now we have Kp. Is there a relationship between those two? Part C. Converting Kc to Kp. I'll give you the equation, and then if you need to convert in the other direction from Kp to Kc, you have techniques to do that. Either you rearrange the equation. I actually like to plug in the numbers and then simplify. I don't normally like to rearrange variables. I like to plug in numbers as quickly as possible. But anyway, I'm not going to show the derivation, but Kp can be calculated if you have a Kc. You're going to multiply by RT raised to the power of delta N. Okay. Let's talk about these numbers. So again, you have Kp, Kc. The Ks are unitless again. Don't have to worry about the units. R. Kp was in practice measured or calculated using partial pressures in atmospheres. R is going to be the gas constant, the one using the liters atmosphere, mole dot K. T obviously should be K. Oh, what is that? Delta N is the difference in the number of moles from products to reactants. Number of moles of gas in products minus number of moles of gas in the reactants. Okay. And delta N can be negative. Don't worry if it is negative. So if you have 3 moles of gas in the product and you're minusing 7 moles of gas in the reactants, your delta N is negative 4. So don't worry that you can have a negative exponent. Delta N can be negative. Now, like I said, if you're given Kp and you want to calculate Kc, I know that some students want to go ahead and rearrange the variables. I would rather just plug in the numbers first, combine terms, and then solve for Kc. Is there anything else I need to say? There is something that I totally forgot. Oh, what's interesting is if the delta N is 0, then that becomes 1, and Kp equals Kc. So Kp actually does equal Kc if you have the same number of moles of gas on each side. Now just keep in mind that the reaction should have only gas in the equilibrium expression, no aqueous. And this is still valid because even though we have a liquid, the only thing that shows up in the expression are the partial pressures. So you see the dilemma. If there was something that's aqueous, then where would you put it? Because something that's aqueous should be put in the equilibrium expression because it is changing as the reaction is headed towards equilibrium. Anyway, Kp equals Kc if same number of moles of gas in the products and reactants. Or you could say on product side and reactant side. I believe that's all I want to say about Kp. We're at the point in the unit where now we're going to be looking at fairly sophisticated problems where we have to figure out now partial pressures of multiple compounds or concentrations of multiple compounds, meaning that you have more than one variable that's unknown. That will be in the next 2 or 3 videos.